Hello everybody, I will start my today another live coding session. So in my today's session, I will solve this question. Count complete tree nodes. So in this question, I'm given the root of the complete binary tree and I will return the number of the nodes in the tree. According to Wikipedia, in a complete binary tree, every level except possibly the last is completely filled in. And all nodes in the last level are as far left as possible. It can have between 1 to 2 to the power h nodes, inclusive as the last level h. Yep. Okay. In this question, I will think of the complete binary tree. And as the input, I will be given the root of the tree. So the input should be tree node. And for the output, I will return the number of nodes in that tree. So the output should be an integer. Okay. And from the constraint, I can find the number of nodes is from 0 to 5 to the power 10.5 times 10 to the power 4. So maybe there isn't any node. In that case, the given root should be none. In that case, I will return 0. Okay. Good. Okay, so what I will do in this question seems to be quite clear. So I will think of this question with an example. So the example 1 with the graph seems to be a good example. So I will use this. Okay, so in this case, yeah, as I can see, for the first level 0, all the nodes are filled. For level 2, all the nodes are filled. For level 1, all the nodes, 2 nodes are filled. And for level 2, not all the nodes are filled, but 3 nodes as left as possible are filled. So this is, I can say, complete binary tree. And I will return 6 in this case. Yep. So obviously, the approach I can use for this question is the recursion. Yeah. And the recursive functions interface should be like this. The argument is the root node, and then returns the number of nodes in that tree. Yep. And with this, for example, if I'd like to know the number of nodes under root 1, firstly, I will recursively find out how many nodes there are under node 2, and also how many nodes there are under node 3 by calling this numNodes recursive function. And then with those results, I can say 1 plus numNodes root 2 plus numNodes root 3 is numNodes root 1. Yeah. So in that way, I can, recursively solve this question. Okay. So in this way, the time complexity should be O of n, because for this argument root, it can be any of the node in the tree. So there are n nodes. Yeah, n possible argument. And for each recursive function call, it takes basically the constant time aside from another recursion call. Yeah. So the time complexity should be O of n, which is n times 1. Yeah. Yeah. So just to be clear, once I calculate the result, I don't have to calculate anymore. And that's why I'm saying I'm thinking of the time complexity, which is used aside from the recursion call. Yeah. And for space complexity, this should be O of log n, because the height of the tree is almost log n, and the recursion stack, number of the recursion stack should be exactly the height of the tree, so it should be O of log n. Okay, this is it. Good. So from here, what I will do is, I will start implementation. By the way, I will implement the count nodes, but this is actually the recursive function I've just explained in line 7. So I can make this as a recursive function. I don't have to, create another function which should be recursive. This is the base case. Yeah, so this is the, ordinary case. Okay. I execute my code. Good. Yeah, it's accepted. So this is good. However, the Rust line says I have to design algorithms that runs in less than O of n time complexity. So I have to optimize this. Okay, so let me think. So how can I optimize this? So my idea is that I can use binary search. So I will think with this example. So I can easily find the height of this tree, and also I can find if this is a perfect binary tree, how many nodes there are with that height. I can easily calculate it by math. Then what I'd like to do is I want to find out how many nodes are missing in the bottom level. Then I decrement, I subtract that number from the number of nodes in the perfect tree. Then I will return it. Yeah. So I can say, sorry. Yeah. So this is the basic thing I can do to calculate number of nodes. And so far, this takes only log n time. So sorry, I say, oh yeah, number one, this take log n time because I just have to traverse the nodes in the say left most paths, and I can find the height in log n time. And for this one, I can do it in the constant time. I will do some math. And for number 4, this takes constant time. And for this one is a bit challenging. And I try to make it smaller than log n. I mean, faster than log n. And so now from here, I will think how I can do number 3. So to find this, I would say I will think of the index of the last node in the bottom level. By the way, in the bottom level, there are, how many nodes there are? Because this is height 3, I can say this. Okay, so if the height is h, then I can calculate the number of nodes in the bottom layer as 2 to the power of h minus 1. That being said, I will think, where is the last node? So this is what I'm interested in. So probably I can use the binary search. So firstly, I can't say anything. So the last node should be in the range of low to high. Then I somehow traverse and find, say, middle node as node 5. And if the middle node is node 5, then I can say, I can say last node is this or later. And if middle node is equal to x, which means if somehow I identify the middle node, which is in the range low to high, and around the middle center, then if that node doesn't exist in the lowest level, then I can say last node is before this. Yeah. Or I should say left hand side of this. So with this, so I can say something like this. So in this way, I can, scope down. I mean, filter the range of low to high, reduce the range of low to high, and then finally, if low is equal to high, that is the last node, the lowest level I'm looking for. Okay, so that's basically the idea. And still, there is one more thing I have to take care. How can I reach the middle element? So firstly, I think this is easy. Maybe I will go to the left once, then right as much as possible. Yep. And if there is, I have to think of the node which is before this. So okay, let me think of the bigger binary tree. Okay, let me think with this case. So in this case, the missing number is here and here. And let me remove here. Okay, so these three numbers are lost, missing in the lowest layer. So with that being said, firstly, low is here and high is here. Yeah. Then from here, the first thing I'd like to do is find the middle node. As I said, I can do first we go left and keep going right, and then middle should be here. Then here I can say, this is the node, existing node. So I can say low is middle, so low becomes here. Then, because I'd like to, reach the middle of this node, or maybe I can say, instead of this, if there is, I can say the last node should be this or later. So this or the last node in this subtree 3. Yeah. Oh, and one more thing I can say. Okay, so I can think of it in another way. Yeah. Even though this is a binary search, so way to find, okay, this is a kind of binary search that I don't have to think of the middle. Instead, what I can do is, first tree, I will think of the tree. And my goal is to find this node, 12, index of this. So for this, I will go left, then keep right. So in this way, I reach node 11. And if it exists in the lowest layer, I can say the last node should be this, or last node in root to the left, not root to the right. Yeah. Go left and keep right. So if, yep. So in this case, if this 11 exists, the last node is maybe it on in the node subtree whose root is 3, or if it doesn't exist, if the bottom node doesn't exist in the subtree, I will return the node which I've just found. Yeah. And if it's missing, I will return, because for example, if this is missing, I can say the last node should be before this. What can I do? Or, I mean, at least I can say last tree is in under root 2. So I can say this. last bottom node is under root 2. Okay. So this is kind of implementation for last bottom node method. Okay, then with this, I can calculate the missing nodes in the bottom level. Yeah, that's it. Okay, so in this way, when I take a look at this function, the last bottom node, this is actually the recursive function. And every time, as I can see from this, root.right or root.left is an argument of the recursive function. This means that the kind of range I have to take care in each recursive function becomes half by half. And finally, it becomes the only node. That's the end. Probably this is the base case. Yeah. So in that way, the time complexity of this last bottom node is log n. No, I mean, so basically, I have to call this last bottom node log n time, but every time I have in line 44, I have to traverse until the bottom. So firstly, maybe if the remaining height is 5, it takes 5 times. Yeah, sorry, it takes 5 times. 5 node traversal. Then the next in the next recursive function, the remaining tree height is 4, and I have to traverse until the bottom, so it should be 4. So it should be 5 plus 4 plus 3 plus 2 plus 1, in my understanding. Yep. So it should be this. So this should be, because there are log n element, 1 plus log n times log n divided by 2. This should be log n times log n, which is less than O of n. Great. Okay, so I start the implementation. So now line 17 is done. First line 18, find number of nodes in perfect tree. If height is 1, it should be 1. If height is 2, it should be 3. If height is 3, it should be 7. So I can say it should be 2 to the power of h minus 1. Okay. Then in number 3, in line 19, finds the number missing nodes in the bottom level. Okay, so in this way I can count missing count. Then where we return is this. Okay, so now I finished some implementation of the main method. Okay, and I will implement two sub methods for number one height. I can count it in this way because I don't have so much time. I will, yeah, go to the missing count in bottom. So um here, okay, wait, I actually don't have to this Rust bottom node. Instead, I will make this like this. Yeah, for to missing count in bottom. If the node, yeah, I will think of the same way. If I go left and keep going right, and if the node exists, I can say missing count in bottom is root.left. Yeah, root.right. I mean, missing number count in the root.right. And if it's missing like this, in that case, yeah, at least I can say last missing count bottom in the root.left. So, no, plus bottom num in left. This. So if this is missing, the missing count should be that this plus missing count in the subtree 2, which is rooted to left. I will implement it this way. But, and also one more thing I have to take care is that I always have to take the argument height of the tree I'm thinking. For example, if I'm at the node 3, I have to know what I'm thinking. The tree I'm thinking is height 2 or height 3. Because if height is 2, I can say there is no missing nodes in the bottom. But if height is 3, I can say all of the nodes are missing in the bottom. Because that kind of height is important. Okay. So as the base case, if this is root is yeah. If height is 1, I will return this. So if root is none, I return 1 because that node is missing. Otherwise, I will return 0 because root exists, which means that there is a node. And the perfect binary tree of the height 1 is completely filled in. Okay, so this is a base case. And otherwise, as I said, okay, I move the cursor. And again, I have to think I have to move the current, pointer here in line 74. Okay, so I mean, if height is h, in line 44, go left once, and then go right h minus 2 times. And maybe this is none. Okay. So in line 74, current dot right is not none. No, as I said. Okay. And here this current is none or existing node. So as I said in line 55, if this is existing, let me go with this case. So if current is none, in line 45, if this is missing, I will return this. Yeah. So here, bottom count in root of the right tree. The bottom of the right root of the right tree is height minus 1. So bottom count in right is equal to just like this. Okay. I can say this is what will be returned. Okay. Otherwise, because current node exists, this is the case when like this exists. I just have to count the number of missing nodes in the root of the left. No, sorry, root of the right. Okay, so this is it. So for time space complexity, what I need is only the recursive function, and the recursive function recursion stack, and recursive function can be up to log n call, which is height. Yeah. Because as I can see from the implementation of missing counting bottom function, when I call when I call this function recursively itself, I always call with root dot left or root dot right. Every time I call the recursive function, I go one level lower in the tree. So in total, it should be log n call, which is the height. Sorry, I'm log n recursion stack. Okay, good. Sorry, my screen was not shared this time also. Oh my god. So let me explain what I did so far. So where was I? Yeah. So I gave up the idea of using low and high, and instead, so I will delete this. Oh, I don't have to delete this. Just delete this. Or this. Yeah. I decided to think of the missing counting bottom function. This is recursive function. And I try to take a look as a center node in this tree, like this in this case 9. For that, I go to from the root, I go left once and then keep going right as much as possible. And finally, this reaches some node or maybe null. So if this is null, this means that the missing count is number missing node in this subtree 2, which is root dot left, plus all the bottom nodes in root dot right. Yeah. So that's a case when this center node is null. And if this is not null, the number missing node in the bottom is exactly the number missing node in the root dot right. In this case, 3. So I will call this. I will think of this recursively. Yeah. So in that way, I can formalize a dynamic programming equation in this way. And the time complexity is log n squared. And space complexity is O of log n. And this is my implementation. Sorry, I couldn't share my screen. Okay. So this is exactly corresponds to step 1, 2, 3, 4. And this is height. Yeah, this is very easy and fundamental. And for missing count in bottom, yeah, I just coded this logic. Yeah. So as I can see here, oh, this is a base case. If height is 1, yeah. If that root exists, I should return 0. And otherwise, I should return 1. And then in line 69, I move the cursor. And according to if the cursor is null or not, I will call this function recursively in a different way. Okay, so let me submit my code. Oh, hide this. Because height is always one, height smaller. Because I'm taking a look at root dot left or root dot right. So I pass height minus 1. Oh, in some case, root is none. I see. So this is the case when root is none. So if root is none, this goes through, this height is 1 base case. So now it reached here. So what I can do is, in the main method, I will immediately return 0. Okay. So in this way, I can say here, height is 1 or larger. Good, and then submit my code. Oh, wait, this is obviously the typo. It seems like it infinitely running. Okay, I will fix this. But why is it taking so long? Wrong answer. Okay, so let me take a look at this case, 1, 2, 3, 4. So what I can do here is, firstly, I will check this and this. to find out which part is wrong. And I can see 7 and 4. So yeah, this case 1, 2, 3, 4 it looks like this. And yep, number if pocket should be 4 and missing count should be 3. So 0 is okay. This is okay. Oh wait, missing count should be 3. Yeah. So missing count part is wrong. So I can say I have to fix this. So I will print out the argument and the returned value from here. Wait, so okay. Root dot wait, root is none. Okay, I see. Okay, what should I do? Let me go with this. Okay, I can use this for debugging. So first 3, if root is none and height is 1, missing count is 1, this is correct. And if root is 2, let me copy it in here. Okay, so if root is 2, then and height is 2, yes. In this case, missing count is 1. This is correct. And if root is 1 and height is 3, missing count is 4, this isn't correct. So it seems like this part, counting the number of nodes counting the number of nodes under the subtree node 3, this is wrong. So probably it should be this part. Okay. So wait. So I see, I found the reason. It's the bottom counting right. This should be height minus 1, which is 2. Yeah, so the number of bottom nodes is the height 2, which should be Oh no. So my mistake is I referenced line 60 when I implement that, but this is number of nodes. All the number of all the nodes is 3. But in this case, I want the number of nodes in that level only. So it should be 2 to the power of, if height is 1, so wait, bottom counting right. What's the level of bottom counting right? Root right bottom level. This is what I want first. So if height is 2, in this case, in this case, height is 3. But I'm thinking rooted right, so I should decrement height minus 1. Sorry, I have to subtract 1 from height. Then I get the height level in one index. Oh, wait, used. Sorry, so this is root. This is rooted right. And now height is 3. And my concern is this. Oh, sorry. Okay, so when I think of this, so I can say this is level 2, which is 3 minus 1 in one index. Or I can just say root right height. This is more easy to understand. Yeah. So if root right height is height minus 1, so this is height. And if the say height is 2, the bottom count should be 2 to the power of height minus 1. Yes. So this. Yep. So if height is 2, the bottom count is 2. Yes. If height is 3, bottom count is 4. This is correct. Okay. So with this, I can say this should be used here. And I submit my code again. Good, accepted. Okay, so I submit my code again. Great, and now it's accepted. Okay, so I quickly wrap up my today's coding practice. So today I solved the question, count complete tree nodes. And in this question, I'm given the root of the complete binary tree and I will return the number of nodes in the tree. And my first approach, which takes log n O of n time, linear time, is just using the recursion, which is very elementary and fundamental idea. And also I optimize this to for the time complexity to be log n times log n. In that approach, I use the kind of binary search. Yeah. So I can say in core, my concern is how many nodes are missing in the bottom. And to find out that, I use the recursion. Yeah. And so for that, if I try to find the number of nodes missing in node in some tree, then I will go to the kind of center position of the leaf nodes by going left once and then going right. Yeah, height minus 2 times. Then according to that node, if it is missing, I can say number of the missing nodes is, yeah, in round 40, I can say like this. And if that center node exists, I can say missing count is the number missing count in the root.right subtree. So that's where I can use the recursion, and the time complexity can be log n times log n. Okay, that being said, I finished my today's coding practice. Thank you so much. Bye.